We have looked at the distance vector algorithm before. In this video, we will look at some issues associated with this algorithm, some solutions to the problems, as well as a routing standard that implements this particular algorithm. The usual quiz first. For some of you, it must have been a while since the distance vector algorithm, so let me quickly refresh your memories. Nodes maintain state in the form of routing tables. This contains the destination, cost as well as the next hop, but these nodes exchange the routing table information pertaining to destination and the estimated cost with their neighbors. When a node receives one such message, it is then going to update its own routing table based on the Bellman-Ford equation. Basically, tries to choose the best path to the destination based on its current estimate as well as the information contained in the message. And we also seen that such messages are sent periodically as well as whenever the table changes. Let me flash this also in the hope that it will aid your memory. Moving on, every path has its puddle. We have seen this again and again, and this statement is even more relevant since we are dealing with routing algorithms that capture paths. So what's the problem? What are your thoughts? What can potentially go wrong with the algorithm we have covered so far? So here is the problem. This algorithm unfortunately introduces loops when the network topology changes. So let's look at this example. So in this example, we have 4 nodes. The cost of the links is 1, and this link between B and D has broken, thereby causing the cost to change from 1 to infinity. So here I'm going to show the state being maintained at nodes A, B and C as far as the destination D is concerned. So originally A can reach D via B. So this is what is the state it is maintaining, and similarly this is the state that maintains. As soon as B detects that this link is broken, it is going to update its state and say it is at a cost of infinity. It doesn't have any next hop to reach D. So this link breakage is going to do a triggered update. So B is going to tell A that it is at a cost of infinity to D, thereby A is also going to change it to cost of infinity because it is going via B. So this is the state after this particular message reaches A. Now suppose even before B sent its triggered update to C, C happened to contact A, and this, let's say, is a periodic update where C is telling A, I can reach D at a cost of 2 because that is the information it has. So what A is going to do is fine, I can't reach D, and C is saying it can reach D at a cost of 2 and I'm at a distance of 1 to C, so it will update it to here and change the next hop to C. So after this, B finally sent the triggered update to C, thereby C modified its cost to infinity with respect to D. Now what A is doing is it is sending, because its state changed, it is now going to send a triggered update to B. Now what does B do? It is going to think there is a path to D via A, and thereby it is going to update like this. Now you see what is happening. No one really has a route to D, and each thinks there is a route via some other node. So this problem is called counting to infinity, because if you let this run, finally the cost is going to keep on increasing, reaching infinity. Imagine what happens to the poor packets that come to the routers when this is happening at the routers. Suppose a packet were to come to node A is going to forward the packet to C because that's what it says next hop as. And what is C going to do? C will see it has to go via B, so this is going to come to B, and let's say by this time all this has happened. Now B thinks the path is via A, so it is again going to send it to A, and now A may send it to C, and so on and so forth. So the packets can go in circles when this happens. So how does one solve this problem? What are your thoughts? Do you think a solution is even feasible? One solution is to make infinity small. What? Infinity and small? This is what I mean. Basically used to represent the maximum cost of a path by a smaller number. So for example, you could use 16 to represent infinity, where in this specific case, I am assuming that I am going with a cost metric, which is a hop count, and I am assuming in the given network topology that the maximum number of hops are under 16. So for that particular topology, since between a given node to another node, the maximum hops will not exceed 16. So if you are seeing numbers greater than this, that means that set it equal to an infinite cost. All this does is it bounds the time it takes to count to this infinity. Another approach that is typically used is split horizon. Don't send routes learned from a neighbor back to it. Again, let's look at this specific example. Suppose B to C link has failed and earlier its cost was 1. Before B could send the triggered update to A, suppose A were to send I can reach C at a cost of 2, B is now going to set the next hop to A. Now in response to the message from B, A now is going to think B has a root, B will think A has a root, and this leads to counting to infinity problem. This problem in this particular case can be avoided if before this link even failed, A knows that to reach C, it is going via B. So this is the destination, this is the next hop, and the cost is equal to 2. So since it learned about this information from B, this information A is not going to send to B. So in other words, the routing table update that A sends will not have an entry corresponding to C. An even stricter constraint is to do split horizon with Poisson reverse, where in this case, you send routes learned from a neighbor back to it, but you set to infinite cost. In the same example earlier, A did not even mention about C, whereas in this case, A will mention about C, but it will say I can reach C at an infinite cost. And this is what it is going to send only to B because it learnt about reaching C via B. But it may say to some other node that to reach C, I am at a cost of 2. This it could send, for example, to some other node D. But to B, it will send this because it learned this information from B. Now you must be wondering, what is the difference between split horizon with and without Poisson reverse? Poisson reverse can help in certain specific situations. Again, let me give an example. If I were to ask you to come up with this example, I think you'll have a really hard time, so pay attention. So this is what is happening. Suppose A and B are connected by a link which is extremely slow, whereas these links ACCB are very fast links. And let's also assume that originally A is reaching D via ACD and B is also reaching D via this. Now suppose this link were to fail and C is going to send a triggered update saying that I can reach D at a cost of infinity. So this is going to be sent over these fast links. But just before that happened, let's say A sent a periodic update to B and B sent a periodic update to A, but this is still traveling over this extremely slow link. So what happens is A is now going to set that on receiving this triggered update, A will set that it can reach D at a cost of infinity because it's going via C. And similarly, B is also going to set that it cannot reach D via C, thereby it will set it equal to a cost of infinity. Now these periodic updates that were sent by A and B before they learnt from C about the status of D are going to slowly reach B, and once they reach, now that they have set D is equal to infinity and A is saying it can reach at a cost of 2, it is now B is now going to think that it can reach D via A, and similarly A is going to think that it can reach D via B. So each thinks it can reach via D with each other. Now if split horizon were used, note that we are not using Poisson reverse. Since A thinks it can reach D via B, A is not going to inform B about reachability to D, and similarly B is not going to mention D as part of its routing update. So A and B will continue to think that this path is valid. Whereas on the contrary, if split horizon with Poisson reverse was used, A would have told B that it is at a cost of infinity to D because it learned this path from B. Thereby, B is immediately going to know that it cannot reach D, and similarly A is also going to know that it cannot reach D. So with Poisson reverse, one table exchange itself, you reach the correct information that none can reach D, whereas in split horizon without Poisson reverse, this tail path is going to stay at both A and B for some time. Now, do you think split horizon helps solve this particular problem? Unfortunately, no. So as you work out, you will see that all the message exchanges that are sent are valid as part of split horizon, but even then this counting to infinity has happened. A solution that works but slows down convergence is the hold down timer, where basically a node waits for some time before propagating link failures. So what do I mean by this? Again, look at this example. A, when it heard from B, it set a cost of infinity, and as soon as C told that it can reach, it changed the cost to 3 and set the next hop equal to C. When you are implementing hold down, since A has just heard about a cost of infinity to a specific destination, it is not going to act on this particular message. It will wait for some time. And hopefully what would have happened is then B would have told C, and C would have set it equal to infinity, and C would have told A also that it cannot reach. By this time, things would have converged. But the problem with this is because now you are waiting before you are propagating your changes in your routing table, it slows down the convergence of the algorithm. There is another method to avoid this looping problem, that is a path vector routing, a variation of distance vector. So in path vector, what you do is whenever you send your routing table information to your neighbors, you just don't send the cost, but you also send the entire path to the particular destination. Now, how does this help? Suppose A is reaching destination D via B. So when A sends a routing message information, it will say I can reach D via some cost, and the path I am taking is basically A, B, C, D. Now B, for example, if something had gone wrong and it is not able to reach D, let's say this link has failed, it knows not to use this path advertisement from A because it sees itself as part of the path. Thereby it is not going to act on this particular message from A. So great idea, it avoids the looping problem, but what is the drawback of this approach? Basically too much overhead. Now the information that you have to pass has to have this entire path information, and this takes up many bytes. So in spite of all these problems, this distance vector routing algorithm was actually implemented as a standard, and the standard is the Routing Information Protocol standard. This is one of the oldest distance vector based protocol. It was very popular, but these days it is not used because of these convergence problems. And this compound when the size of the network is really large, and that's what we see these days. So here are a few features of this RIP protocol. The routing message exchange happens via UDP transport protocol. So this is running as an application layer process where the port 520 is reserved for this particular application. Notice it is creating forwarding tables for the purpose of routing, but it is doing this as an application process. So as part of this protocol, these updates are sent periodically every 30 seconds. This protocol also supports multiple address families, by which I mean not just IP, it can support other address families as well. It does a hop count, thereby the cost of a link is 1. It basically tries to find the minimal hop count. And as part of this protocol, to speed up convergence, the 16 is set as the value corresponding to infinity. This is how it counters the count to infinity problem. Apart from this, this also supports split horizon and the hold down timer. As you can see, since you're using 16 to represent infinity, RIP can run only over very small networks where the maximum hop count is under 50. So here is the RIP packet format. RIP has other versions, but we will focus on version 1. Now is also a good time to put theory into practice. So far in the description of the algorithm, we have been dealing with routers. In fact, the state that is maintained at a given router itself is something of this, where you are specifying that to reach router R1, it's a cost of C1, and to go there, you need to go via next hop 1, which is another router. But when we talked about forwarding and addressing, the information that is maintained as part of the forwarding table is basically an IP prefix and the next hop that leads to this particular IP prefix. So this is related to the address portion and this is related to the next hop router. So how does one relate with this routing table information with the forwarding table information? Well, it's not very complicated. Typically what happens is a given router serves different networks corresponding to different IP prefixes. Suppose this router is serving these two organizations with IP prefix 1 represented like this and IP prefix 2 represented like this. So when this router is advertising to its neighbor its routing information, what it advertises is not that I can reach R at a cost of 0, but rather I can reach IP prefix 1 at a cost of 0, I can reach IP prefix 2 at a cost of 0. Now this router could have heard from its neighbor R1, which is directly connected to IP prefix 3, in which case this router can also advertise that I can reach IP prefix 3 at a cost of 1 because it goes to router R1 at a cost of 1. So this is the information that is actually exchanged with the other neighboring routers. But this next hop information that you maintain will be that of the router from which you could reach this particular prefix. So this is captured in the RIP packet format itself, where you're not advertising the router, your neighboring router information, rather the IP prefixes. So let's look at the fields one by one. So the first field is a command field. This could be a request or a reply. So often a router could request its neighbor's routing table information, in which case it sends a request and the neighbor will reply to that request with a reply RIP packet. The periodic as well as triggered updates are basically replies that do not have a prior request. Like we have seen in IP versions, RIP also has different versions. So there is a field that captures which version of RIP we are following. These are reserved, so we'll talk about it later. Now following these first 4 bytes, so this is 0 to 31 like before, are set of entries, and you can have up to 25 sets of such entries. Each entry itself is 20 bytes long. So this is 5 into 4 bytes. The first field within this entry is the family of the network. This is used to indicate which protocol you are following. Since we are following IP, so this is set equal to a value that corresponds to the IP protocol. So this shows that RIP can potentially be used over other network layer protocols also, not necessarily IP. Following this is the address of the network. So this is the network portion. In RIP version 1, we are still dealing with class full addressing. So there was no net mask. We don't need to carry the mask information that. And then it also specifies the distance to this particular network. And these entries repeat. What if you have more than 25 routing entries within your routing table? Then you need to send it over multiple RIP packets. As you can see, there are many empty fields as part of this packet format here, 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 here. The reason why these are arising is, as I mentioned earlier, this can support other family classes, and if those other family classes have an addressing scheme that is more than 4 bytes, you can use this additional information. In fact, when one moved on to RIP version 2, which had to handle classless addressing, these fields, these reserved fields, were used to specify the mask information. I won't get into more details than this. So here is a summary of what we have seen in this video. Distance vector is a distributed dynamic algorithm that exchanges information locally to determine the least cost path between the nodes. Unfortunately, it suffers from poor convergence and routing loops. There are certain partial solutions to the problem in the form of split horizon, hold down timer, making infinity small, so on and so forth. RIP is a standard that implements this distance vector protocol. It handles some of the above problems via these techniques that I have mentioned earlier. All said and done, it has convergence issues, as well as it can be used only over routing domains where the maximum hop between routers is under 16. The better approach is link state routing, which is what we will cover next.